Welcome to Video Notes 1.1. So what's going to happen in video notes is that I'll give you the list of objectives for the video, and you can write down as much or as little as you want, but it's a good idea to listen. So besides taking notes from the PowerPoint and the video I'm doing, please also read pages 78 to 88 and 96 to 99 and take notes from the book. Definitions, examples, those kinds of things will really help. Okay, so early models of the atom. So the first simplest kind of atoms people thought existed were indestructible spheres. And so a lot of times you'll hear that referred to as Dalton's model. And it does go way back to ancient times, but real atomic theory and with evidence to support it dates back to Dalton in the 16th century. So Dalton's model, hard indestructible spheres. But then some more experimental data came along showing that atoms have negative charge. If they have negative charge, they also have to have positive charge. This is also often called Thomson's model. And it shows the presence of positive and negatively charged particles within the atom. And then more data was collected through experimentation, and another model of the atom, a later model, Rutherford's model, often called the nuclear model, or this one's called plum pudding model. And Rutherford's model is the nuclear model because it was the first time there was evidence of something very small, dense, and positive in an atom, and those electrons are still there. So with all the progression of atomic theory, we get to the Bohr model of the atom, which still has a nucleus that has protons and neutrons in it, and then electrons, Bohr thought, were in energy levels orbiting outside the nucleus. Okay, it's almost right. There's protons and neutrons in the nucleus. There are electrons outside the nucleus, except no orbits. So Bohr's model was able to explain a lot of things about atoms, but it didn't explain them all. And so his ideas that electrons were orbiting the nucleus are incorrect. We often use this to symbolically represent what we think atoms look like, but just remember that rings are wrong. There's no orbits. We have our current model of the atom, which is called the quantum mechanical model, sometimes called wave mechanical model. Sometimes, like I said, called the wave mechanical model, based on data and evidence from Schrodinger and Heisenberg, quantum theory, but it's still nucleus with protons and neutrons in it, electrons outside the nucleus. They're not in orbits. They're in probability clouds that are called orbitals. So there are energy levels. Electrons have different energies, and those electrons can exist in certain energy areas called electron orbitals. And that's what we think atoms currently look like. So here's the main ideas, though, about atoms that are going to help us understand chemistry right now. Protons are in the nucleus. They're positively charged. They have a mass of 1 AMU, and we can talk about that in class. But usually protons tell you the identity of an atom. Neutrons also in the nucleus, that center part that's positively charged, but the neutrons are neutral. They have no charge. They also have a mass of 1 AMU. And a neutron, the neutrons give atoms their mass. Well, so do protons, but neutrons help in stability and mass of an atom. Electrons are in clouds outside the nucleus. Those clouds are called orbitals, described by probability. Electrons are negative. They have negligible mass, meaning that if you compare them to the mass of protons and neutrons, they're about 1,000 times smaller in mass. So we say they have almost no mass compared to the heavy parts of the atoms. They give you the charge of atoms, and negligible means they don't matter much in terms of mass of an atom, but they do matter in lots of other ways. So here is another model of atoms. They're neutral building blocks of the elements. Remember, atoms are neutral. So here's a picture that can help you understand atoms. But it's very off scale. Okay, so this is nowhere near the scale. And look at these rings. We know rings are wrong, but they do help us locate electrons when we're drawing a model. Okay, So the nucleus is the center part. Right? Center part. Okay. The nucleus has protons. Protons are the positive parts. The neutrons are the neutral parts, no charge. And then the electrons are the negative parts. So atoms are neutral because their number of protons, 1, 2, 3, 4, 5, 6, equal their number of electrons, 1, 2, 3, 4, 5, 6. So atoms are neutral. So why is an atom neutral? Because the protons equal the electrons. So what happens when that doesn't happen? Well, you have what's called an ion. Vocab word, big word. Atoms that are not neutral, they have charge, okay, overall charge. So let's look at this. Na is sodium. Right here's the nucleus, so there'd be, oh, I can't see that because I wrote it in red. There's 11 protons in the nucleus of sodium. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. So this is an atom of sodium. Okay, but let's look at this. It says Na, but here's this plus sign. So 11 protons again in the nucleus, or else it's not sodium. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 electrons. And so, since there's one more proton in the nucleus than there are electrons outside, this is an ion because it has a charge overall. Okay, but protons can't change for an atom. Electrons can. So somehow from here to here, one electron was lost to turn it into the sodium ion. Okay, let's check out this one. It's nitrogen, so we have 7 protons in the nucleus. 2, 4, 5, 6, 7 electrons. 7 electrons. So this is nitrogen. It's a neutral atom. Nitrogen atom. If you go from there to here, you still have 7 protons. It means it's nitrogen. There's 1, 2, 3 extra electrons. So it's a -3 charged nitrogen ion. So nitrogen ion called nitride, by the way. And this is just called sodium atom. So what do we call it when an atom turns into a positively charged ion? It's called a cation. It's a cation because cations are positively charged. Get it? Positive cation. Okay. Anions are negatively charged. So this example here is a cation because it has a positive charge, positive, which means electrons have gone away. This is an anion because it has a negative charge and it has 3 extra electrons in this case. All right, so what information can the periodic table tell you? Well, it can tell you the protons in an atom because atomic number is protons. So nitrogen is nitrogen. Any atom with 7 protons in its nucleus is nitrogen no matter what. Okay? You can also find out all of these other things about an atom. So here's a way to symbolize a type of atom. Here's the name of it. Chemical is uranium. It's not the name, it's a symbol. And then this bottom number is the atomic number. Okay, it's the number of protons. This top number is called the mass number. And the mass number is protons and neutrons added together. So it's the heavy parts of the atom, gives it its mass, and then the chemical symbol. Okay. So isotopic notation. If you want the name of an isotope, I'll use the one on the other slide, uranium 238. You might be saying, what? So if you look here, this is uranium, and then the 238 tells you the name of the isotope. Okay. The symbol for that isotope is U for uranium, 238, and then, so the dash is the mass number, and then 92 is the atomic number from the periodic table. So if you want the name of an isotope, you write the name of the element and its mass number. If you want the symbol of the isotope, you write the symbol of the element, its mass number upper left, its atomic number bottom left. Okay. So if there's no indication of charge, then it's going to be a neutral atom. Okay, so let's play atom or ion. This must be an atom because there's no charge. Right, this ion, because it has a charge. In fact, it's an anion because it's negatively charged. This is an atom. There's no charge. This is an ion. Charge. And it's a cation because it's positive. Ion. Ion. Okay. So if you see the charge up next to it, it's an ion. If you don't see anything, you can assume it's an atom. Now, looking at the isotopic symbol of an atom or ion, you should be able to tell how many protons neutrons and electrons are in it. Protons are positive, neutrons are neutral, electrons are negative. Okay, so how many protons in this? 7, because the atomic number is proton. Neutrons is this plus, so it's 7 plus x equals 12. So that number is not 12, it's 5. So there's 5 neutrons in that, because this is total. Okay, electrons, since there's no charge, there's 7. Protons, neutrons, electrons for this one. Right. Well, let's see. 8 is protons, because its atomic number is always 8. 16 is the total of protons and neutrons together, so there must be 8 neutrons. And this is -2. So there's 8 protons, but if there's -2, that means there's 2 extra electrons, so there's 10 electrons. So for ions, protons and electrons are different. For atoms, protons and electrons are the same. So we have protons, 11, that's this atomic number. Neutrons is 12, because 11 plus 12 equals 23. And then electrons, well, there are 11 protons, but it's a positive sign there, so one of the electrons went away. Okay. How many protons and neutrons, electrons are in this? Well, this says chromium 52. So I go to periodic table, look up on periodic table, I find out chromium symbol and its atomic number, and then I know 52 is the mass number. So there are 24 protons. 52 minus 24 is 26, 27.8 electrons, 28 neutrons, sorry. And then electrons, 24. These are equal because it's neutral. In the end, symbol Ne, the mass number is 20, atomic number is 10. So this one, there's 10 protons, there's 10 neutrons, and there's 10 electrons. Ooh, they're all 10. Okay, potassium symbol. Okay. Potassium ion is a +1. Now I'll teach you how to do that in class, so trust me for now. So this is the symbol for potassium ion. Protons, there's 19. Neutrons, there's 21. And electrons, since there are 19 protons, but this is a positive charge, there's only 18 electrons. So, so I throw that in there to surprise you. Okay, how do atoms of an element differ? So these are all oxygen. How do I know they're oxygen? I'm telling you, it's oxygen, oxygen, oxygen. So what's the same about them? Well, all of these have 8 protons because they're all oxygen. Guess what makes oxygen oxygen? Protons. So this number is the mass number. So this one has 8 neutrons. This one has 9 neutrons. And this one has 10 neutrons. So they're all oxygen, 8 protons, but some are heavier than others. That's what an isotope is. Atoms of an element with varying neutrons. Varying neutrons. Spell that right, Hard? Okay. All right. So what this means is that most of the oxygen in the world is oxygen 16. If I hand you some oxygen, you'd be like, okay, now I can breathe. And then you'd be like, I bet most of this oxygen you just gave me is oxygen 16. There's a little bit of oxygen 17 and a little bit of oxygen 18 in any sample of oxygen. So, why isn't the atomic mass on the periodic table a whole number? Atomic number is a whole number because that's protons. So why isn't it the atomic mass a whole number? Because you know how oxygen has 3 different isotopes? Well, when we take an average of those isotopes to get the mass. But it's not a straight average. I don't take these 3 numbers, add them up and divide by 3, because that wouldn't really represent oxygen. I have to do a weighted average. So a weighted average is taking into account all of the isotopes of that element and their abundance. Okay, so you could look at the periodic table and figure out the most abundant isotope of that element. So I'm going to talk about aluminum. Aluminum has 2 isotopes that are prevalent, aluminum 26 and aluminum 27. Which is the most abundant isotope of aluminum? Well, if we look at the weighted average of aluminum, we find out it's 26.982. This rounds to 27, so 27 is probably aluminum's most common isotope, aluminum 27. Let's try for silicon. All right, silicon, I know, has 3 prevalent isotopes, silicon 27, 28, 29. You look at silicon's average atomic mass, you see that's 28. 0.086, so probably the most abundant isotope of silicon is silicon-28. For argon, if you look at the average atomic mass of 39.94, so probably its most common isotope is argon-40. Okay, see if you can figure out the most abundant isotopes of phosphorus, chlorine, and sulfur. Good luck. Okay, so when we go to calculate the average atomic mass, which you'll have to be able to do, you have to know something about the atoms, like how much each isotope weighs and what percent it is in nature. Okay, and once you know that, you do what's called a weighted average. So you take the mass of the isotope times its percent abundance, and in that case, I got 15 multiplied 0.26 I take the mass of another isotope times its abundance, and I find out that 0.647324. Mass times abundance equals 3.59795. So then what I do at the end of that is I add this all together. I get 1599.95847. Okay? And so when I do that, I get this. But I say to myself, wait a second. That doesn't look like a number on the periodic table. But because these are percents, I can divide this by 100 at the end, and I get 15.999 rounded. Okay? So then, hey, look, there's oxygen and there's its atomic mass. So this calculation was how an average atomic mass is calculated. Now, some of you will change it to a decimal before you use it. Some of you will change it to a decimal after. Either way is fine, just got to be consistent. Okay, here's another example. We're not going to do this one. We'll do this one in class to practice, but we'll be able to calculate average atomic mass. So we're learning a lot about the periodic table. So just to review, atoms are neutral, ions have charge, cations are positive, anions are negative, the atomic number is the number of protons, mass number is protons and neutrons added together. So you should be able to write the symbols and names of isotopes and tell how many electrons, protons, and neutrons there are. And then, in order to calculate that average atomic mass, you're going to multiply the abundance times the mass of the isotope and then add them together. Fun times. Make sure you've read these pages and put into your notes stuff that you read from those pages. Okay, so besides the video notes, what I talked about, make sure you take your own notes on those pages. And hopefully you grab the carrot and eat it while you're doing this. Peace out. Here are the objectives again.